so if I was to just quickly run through the definition of the derivative, it's easier than the one we're going to do because the notation and stuff is just easier. But the definition of derivative, we did this. You don't need to write this down again, but we said, okay, if you've got some point x and some second point x plus h, and we've got some function here, and we would like to know, oh, that's terrible. How can I screw that up already? Okay, we want to know the slope. That's not very good either, but we want to know this slope right here at point x, and we say, oh, God, this is not boding well for the rest of the day. Hopefully things improve. Okay, no, that's actually better. That's actually better. So if I would like to do the slope at this point x, we say, well, and this would be the graph of f over here, and we say, well, okay, this would be the y value f of x, and this would be the y value up here f of x plus h. And we'd say, well, we want to do the slope at one point, but guess what? We don't know how to do the slope at one point. There's no formula for slope at one point. Rise over run, of course, the run is 0. It'd be undefined. You can't do slope at one point. How could we do it? Well, we said, let's do slope between 2 points. Let's pick a second point, and let's subtract the y's, and let's subtract the x's. Of course, if we subtract these two x's, you just get h. And then we said, do the limit as what? H approaches 0, because we said let the 2 points get infinitely close together. Now, the 2 points can't officially become 1 point because it's then again you would have no rise over run. But if we let them get closer and closer and closer and closer, we can see what the slope is approaching, and we can do this thing called the limit. And that is the definition of what the derivative is right there, and that's where it came from. We took something we did know how to do, and we used that to help us answer something we couldn't do, which is a slope at 1 point. And that is our goal today. That's what we want to do today. We want to say, okay, we've got an area under a curve. We don't know how to do that area. We can't use geometry. Okay, so how do we write that area under the curve? Well, let's take something we do know how to do the area of, which is rectangles. There's circles, but there's other things we can use, but rectangles are very simple and are going to work fine. So a Riemann sum is like adding up a bunch of rectangle areas. And we got into a bunch of, just like the x and the x plus h, we got to get into that notation. We got to understand the notation for this to all make sense. So that's a lot of what yesterday and today is about, is this notation. So we're going to divide our interval AB into n subintervals with n plus 1 points, because to divide into 4 subintervals, you need 5 points to divide that up. And we're going to label them starting on the left, x sub 0, then x sub 1, then x sub 2, and so forth, so on, all the way to x sub n. N is our number of subintervals. We said delta x sub I will be the width of each subinterval, and c sub I will be any point in the subinterval. Now, we said it might be the right endpoint, it might be the left endpoint, it might be the midpoint, but it could be any other point in between. Well, basically what that means is to add up our rectangle areas just means take that function value, which is the y value, which is the height, times the width, that's the area. Function value, which is height, times the width, that's area. And you just add up all these rectangles. I mean, that's really all it is. It's just height times width, height times width, height times width, area plus area plus area plus area, total area. That's what a Riemann sum is. Okay, so then we had this homework problem. Here's number 1. And we said, okay, we want to do the area from -5 to 5, so here's our graph. And they wanted us to do 5 left rectangles. Okay, so if we want to do 5 left rectangles, we need 6 points to divide that up. So here they are. 1, 2, 3, 4, 5, 6. That divides it into 1, 2, 3, 4, 5 subintervals. Okay, now I skipped a step here. The first thing we actually would do is that. What was that? What was this right here? The delta x, which is the width of each subinterval, right? How wide are the rectangles going to be? Well, if I'm going to do a distance of 10 and I'm going to have 5 rectangles, they each have to be 2 wide. So I went -5, -3, -1, 1, 3, and 5. That's essentially my x sub 0, my x sub 1, my x sub 2, my x sub 3, x sub 4, and there's x sub 5, right? Using that notation. Okay, so 5 subintervals, and we've got those. And then we wrote it out. We talked yesterday about how we want to write these out the long way here, because that's going to help us, as you'll see today, that's going to help us in some patterns that we want to develop and things we want to do. So here I have my 5 rectangle areas all written out. Now we wrote them in F notation, and I want to talk a little bit here in a minute about the advantage of writing this F notation. Okay, height times width, height times width, height times width, height times width, so forth. One of them actually even had a height of 0, right? Because the left endpoint was right there, so there's no height to that rectangle. Okay, we add all those up, we get the area of those red rectangles. Okay, so that's what we were about yesterday. You guys got a lot of pictures drawn. That's what the homework was about, was just getting used to drawing these left rectangles, right rectangles, midpoint rectangles, just getting comfortable drawing them. Not hard once you get the hang of it at all. What just happened? Okay, so we get to, we need to be able to do that. All right, now let's go to number 7 on your homework. Now, number 7 on your homework said the integral of f of x dx, and they wanted you to do 3 right rectangles, correct? All right, now, as I went around, it looked like some of you had pictures drawn for 7 and 10, but you didn't have to. A lot of people in the other class drew pictures, and that's because I must not have didn't tell them they didn't have to. I mean, it didn't say to draw pictures, but they assumed maybe they were supposed to. But maybe I had told you guys that, or maybe you're just better at reading directions. But you did not have to draw the pictures. Now, from here on out, and that's true. If it says do an R3, we write it out, but we don't have to do the pictures. Now, I'm going to show you something here. I don't think it's important that you write this down in your notes right at this particular time. But if we were to look at just a general writing out of a left sum, I want you to look at this and see, does this make sense? Okay? So in a general left sum, your far left endpoint is the first one you go with, right? And that would be x sub 0. So you're going to check at the far left edge, x sub 0, check that height times the width. And then you're going to go f of x1, which is the next width over, check the height there, and x sub 2, and x sub 3, and then finally you'll end f of x sub n minus 1, right? One short of the far right edge, right? Everybody notice that when you did your left rectangle, okay? And when you do a right rectangle, you'll start with 1, right? You won't start at x sub 0 at the far left edge. You actually go over one width, and here's that first width, and then at the right edge of that is where you check your width, or check your height. And so that's f of x1. F of x2, and so forth, all the way to f of xn. Correct? I mean, so that's what this would be in just kind of a general case writing. Now, midpoints are harder to write. Midpoints, you know, you average, basically, the first two, and then to get the middle. Right? Now, most of the time, we'll just do that in our head. We're not going to write this out this way. But most of the time, we'll just look. Well, okay, here you got 1 and you got 2, so halfway is 1.5, right? You'll just average those. But that's what a midpoint sum would look like, kind of in the general case. And then, of course, here's a trapezoid. 1/2 the 2 vertical bases, which would be x sub 0, x sub 1, and then the next would be 1/2 the 2 vertical bases, f of x1. Okay, so again, we got to be at least a little bit comfortable with some of this notation as we go and work ahead today as we go through this. Okay, so that is not something you probably need to worry too much about right now. All right, so here's problem number 7. Now, you did not have to draw a picture, so I want you to think about this. So it doesn't say draw a picture. All it says is here's the integral, here's R3 is what you want to do. Now, what are the different ways? There's 3 that I'm interested in. What are 3 ways or 3 forms that you could be given a function, f of x? One could be a graph, right? That's what number 7 was. They gave you a graph of f of x. What else? A table. A table. That was 25 and 28, right? They gave you a table. You didn't have to do those, but we've talked about, you know, you could, you know. That's going to be part of tomorrow's homework. So if you did them already, you're good. Could be a table. What else? What's the most common? An equation, right? F of x equals x squared. So, as a matter of fact, the title of our book says Calculus from a graphical, numerical, and symbolic point of view. Graphical meaning graph, numerical meaning table of values, and symbolic meaning equations. Okay? So we can be given functions any of those 3 ways. So on this problem right here, number 7, I'm going to pretend that I never knew. I don't even know yet that there's a graph there. Okay? If I was given this information, did I copy this down right? Is this right? Problem number 7? Am I good here? Okay. You should be able to, without even knowing what the function is, write down the beginnings of this problem. In other words, what I did right here, right, in the F notation. Okay? So, oops. Right? And the reason that's important, not only for the patterns and stuff we're going to see later, but it's important because you shouldn't let the format the function's been given to you freak you out about how to do the problem. Sometimes we get these really hard-looking functions or complicated functions, and we get, you know, and then we're like, oh, geez, what do I do, what do I do? It doesn't matter. It doesn't matter here. To write out an R3, I would start with what? F of, well, now wait a minute. Let's back up a minute. What have I forgot to do? I forgot to figure out how wide they're going to be. And sometimes on these problems, even if, sometimes I will draw the beginnings of a picture just to help me. Like I would take this, and let's pretend again, I don't even know what this function is. So I would go 1 to 7, and I might even just put in a fake function there that I don't even know what it is. And I might say, okay, our delta x would be 7 minus 1 divided by 3, which is 2. So my width is 2. So that tells me I'm going to go 1 to 3 to 5 to 7, right? So I might start that way. And since they're right rectangles, I know my first rectangle is going to be at what? It's going to be at 3, right? It's going to be right there at 3. So I'm going to go f of 3 times 2, f of 5 times 2, plus f of 7 times 2. And I didn't really even need this function part written in here, but the 1, 3, 5, 7, sometimes I'll write those down just to help me. But I can write this whether I have an equation, whether I have a graph, or whether I have a table. It doesn't matter, right? Now, the next step then is to take it out of the F notation. And that might mean to find f of 3, you'd put a 3 into the function for x. Or you'd look up 3 on the graph. Or you'd look up 3 on the table, right? Whichever one it is. Well, in this case, we look it up on the graph. So what do we have? That was 3 times 2, and this was, what's f of 5? 6 times 2, and f of 7, 3 again times 2. So we get 6 plus 12 plus 6, which is 24. So the answer is 24. And that's all you need to show. But I would want to see that written down. But okay, so we talked a lot about pictures yesterday. We want to be able to draw pictures. Absolutely. Next quiz, first problem on the quiz, probably. Here's a function. Do a graph 4 left rectangles, or whatever. Right? You're going to have to be able to draw some left or right or midpoint rectangles in a picture like you did for today. Okay? But it's not always necessary to draw the pictures. Okay? If we want to write out the sum, we can just write it out like this. Okay. Now, I would like you to take out your sample 2 packet, please, and go to number 41. It was one of the problems that we skipped. Now again, don't be afraid to stop me at some point along the way today if I get going too fast. Okay? Don't be afraid to say, wait, back up. What was that last thing? Okay? All right, on number 41, go ahead and read it. Okay, so this is very much like 25 and 28, isn't it? Okay, they're asking for what? What approximation? We just got done doing a R3 a minute ago. What are they asking for? M3, right? They're asking for an M3, a midpoint with 3 subintervals, and they even told you the width is 2. Of course, we could figure that very easily, 6 minus 0 divided by 3, so the width is 2. So my point is this. Now, it's a multiple choice problem, so you wouldn't have to show any work, but But again, here in the early stages, and I really think if you're in a habit of writing this out, it really can just help you avoid mistakes. To me, I can just start doing this. And as a matter of fact, I would do this. I'd say, okay, I got 0 to 6. So look at my graph over here. If you're having any difficulty thinking of this, you say, well, from 0 to 6, the width is 2, so that'd be 2 and 4 and 6. So to me, I would just draw myself a little x-axis here. There's my 3 subintervals. Now, where are my midpoints going to be? At 1. So I'm going to have f of 1 times 2 plus f of 3 times 2 plus f of 5 times 2. And notice I have 3 rectangles here. And again, every time you write this out, I want you to be reminded of a rectangle. This is height times width, height times width, height times width. Right? Area plus an area plus an area. All right, now you take it out of the f notation. Well, in this case, that means plug into the table. So f of 1 is 0.25 times 2 is 0.5. And f of 3 is 0.68 times 2. What's that? 1.36. And f of 5 is 0.95 times 2 is 1.9. And we got to add, is this? Oh, this is a calculator. Although it's not too bad. So 1.86 plus 1.9 is 3.76. 3.76, right? So it's just an M3 approximation is all it is, using tables of values. But the important lesson here, I think, and what I've been trying to get across the last 10 minutes, is when we write in L3 and R3 and M3, we can write those out in F notation, function notation, regardless of what the function is, and then we can come in at the end and plug that in. All right. So, okay. So we're ready to go forward here, and what we want to do, let me, you're going to need a nice, clean couple pages of notes here, probably, for what we're about to embark on. Now again, what we're aiming to do here today is get a definition of the integral. Okay, our goal is to write. Our goal is to fill this in right here. Okay, the integral of from a to b of f of x dx is what? How do we get that? And that's like the limit as h approaches 0. You know, that's where we're heading. Okay. Now we're going to take a little side trip later on into sigma notation. Remember sigma notation? Okay. It has to do with adding and expanding sums. Something you did last year in advanced math. We're going to get into that a little bit. Might have done it in algebra 2, maybe. I don't know. Oh, perfect. So as Emily gets settled in here, we're just going to okay, Emily, what we're just getting started to do is write a definition of the definite integral. Okay? All right. Now, and this, what I was saying, sigma notation. So at some point along the way, it's going to become necessary for us to use sigma notation. Or it's going to be helpful to us to use sigma notation. So we'll take a little side trip and review a couple of things about sigma notation that could be helpful, and then we'll come back and we'll be able to finish it up. All right, so we're going to start with this problem right here. Okay, so we're going to start with the integral of x squared dx from 0 to pi. A lot of times in the book they'll label the integral I. They'll call it I, and then just for shortcut can refer to it later. So just so you get used to that notation. But anyway, we're going to have an integral, an area here, and clearly, you know, that's a pretty easy one. We could do fundamental theorem, which, matter of fact, let's just do right now. We're talking about this piece of area right here, okay, from 0 to pi. Let's go ahead and just get that exact area. What would we do? Antiderivative, 1/3 x cubed, from 0 to pi. Plug pi into that, 1/3 pi cubed minus 0 would be 1/3 pi cubed. And what is that as a decimal? Let's get our calculators out here. We're going to do a little bit with calculators too. What's 1/3? Whoops, that's pi cubed. What's 1/3 pi cubed as a decimal?
10.335.
All right. So we know that area there is 10.335, 1/3 pi cubed. All right. What we're going to do first is an R4 approximation. We're going to write out an R4 approximation. By the way, on your calculators, why don't you go ahead and just verify this integral. I'm going to practice here just putting in some integrals, because as we get into later chapters here, we'll be allowed to do that a lot of the time. Just type in, go into your template, find your integral. Some of you maybe haven't done that yet. Go into your template, find your integral, do x squared, 0 to pi, dx, hit enter. You get pi cubed over 3. Okay, you should get pi cubed over 3. Okay, or if you hit a decimal template. Okay, all right. So we got that. All right. So we're gonna do two things at once here. As we go along, we're gonna talk about how we do it without the calculator, and then what it would look like as we punch it into the calculator and verify those two are the same thing. All right. So we're gonna do an R4 approximation here. So again, if I'm gonna divide up this graph here, this pi, right, into so many subintervals, in this case 4 of them, what happened?
Divide up this pi.
That's a good one. Okay. We're gonna divide it. Well, okay. So anyway, first thing we calculate is what?
Well, how's the width?
How wide? How wide? Right? How big each piece will be? Right? Yeah. How wide? And that's going to be pi fourths. Okay. For this particular one, we would have pi minus 0 divided by 4. So we're going to have pi fourths as the width. All right. So my first rectangle will be, the first rectangle height will be what? F of, same thing we've been doing here now. Now it's a right, and now you might wonder, why are we doing R? Yeah, why not left, why not midpoint? Here's why, if we have a choice, a lot of times we write these in terms of right rectangles. And the reason is because we start with x sub 1, x sub 2, and we end up with x sub n. And for no other reason than the notation is a little simpler with rights than it is with the others. But we could do it with any of them. So we're going to do rights. So the first right endpoint is where? Pi fourths. So it'll be f of pi fourths times the width, pi fourths, plus f of, now, stop right there. One of the things I said yesterday is we're going to be looking for patterns, okay? And what you'll find is, yes, pi halves is correct, but it will be easier to see the pattern if we write it as 2 pi fourths. So most of the time in these problems, we will not simplify things because it's actually easier to see the pattern if we don't. Plus f of 3 pi fourths times pi fourths plus f of 4 pi fourths, which of course is pi. And that makes sense because our last right rectangle should end at the far right edge, which is at pi. Okay? Now, we're going to go ahead and calculate this out by hand. Okay? So that would be, what does f of pi fourths mean? It means pi fourths plugged into the function. So get your calculators out, and let's go ahead and let's type this in. Then I'll show you a way we can do a little quick. Now I said by hand. Well, we're still going to use the calculator for pi 4 squared and stuff like that. But I want you to take pi 4 squared times pi 4s plus 2 pi 4 squared. Now, if you want to do pi halves there, that's okay. It makes it easier to type in. But let's take and let's actually type out all 4 of those. Now this will be the last one of these we type in quite this long. And I'm going to show you, I kind of mentioned the shortcut yesterday. Anybody get something?
Do you want the decimal?
Give me both. Give me the non-decimal.
Okay, 15 pi thirds over 32.
15 pi cubed over 32. That sounds right. And as a decimal?
14.534.
Now, does that make sense that that answer would have been bigger than the exact area we calculated earlier? Because? Since that graph is increasing, picture your right rectangles on here. They're all going to be above the curve, right? They're going to be over approximations. So it makes sense that this was an over approximation. Okay? All right. Now, leave yourself a little bit of room there. And now we're going to do R100. Okay? Oh, wait. Back up a minute. Back up. Well, no. No, that's fine. All right. Now, we're not going to write out 100 or anything. Okay? So we're going to do like the thing I showed you earlier. We're going to write the first couple and then dot, 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 and then we'll write the last one. Okay? So what will change now? The width is now not pi over 4, pi over 100. What's the first right rectangle height going to be then? F of pi over 100 times the width, pi 100ths, right? But your first, now again, I made this easier because we started the integral at 0, okay? So our first right endpoint will be 1 width over, which is pi 100ths, and we'll plug that into our function to get our first right rectangle height, right? And then the next one is f of 2 pi over 100 times pi 100ths. Plus, and let's write one more because it's going to make it easy to see. And notice again, I did not reduce 2 pi 100ths. That would make this problem harder if I did that. Okay, and then we'll go dot, 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 dot. And then the last one will be what? 100 pi over 100, which of course is pi, which we want it to be. Our far right edge is still pi. So we still want the last one to be at f of pi, which it would be. Now, of course, this brings up a problem typing into our calculator because we'd have to type 100 of these. So we don't want to do that. So, and even if we did a little bit of a shortcut here, we wouldn't be able to type this in very easily to get an answer there, right? So then the question becomes, how can we easily add a bunch of things together? Sigma notation. Sigma notation is helpful in doing that. So we're going to take our little side trip here and go back. Oh, that's right. Going to go back to last year and maybe a little bit of Algebra 2. I don't remember if you did any. You might have done this in Algebra 2. But this is sigma notation. Now, sigma is a Greek letter S for sum, okay? And we have these index that they call them. And a lot of times they use lowercase I, lowercase j, lowercase k. Those are the most common indices. Is that plural of index? That they use. All right. And so what this means is we're going to start I as a 1, and it always goes by 1s. So I will be a 1, then a 2, then a 3, then a 4, then a 5. We'll plug those I values into the formula here, and then we will add those together because sigma means sum. So we put in a 1, and we get 4. And we put in a 2, and we get 5. We put in a 3, we get 6. Put in a 4, we get 7. Put in a 5, we get 8. And then we add those terms together. So that adds up to 30, I believe. Okay? And the one down here, 2i plus I squared. We notice that you don't have to start the I at 3. And for those of you that were in computer math, might think of like a for next loop. Well, for next loop, we could go by 1s, we could go by 2s, we could go by 3s, we go by negatives if we want to. Can't do that with a sigma notation. It's got to go by 1s. You can start it wherever you want, but it's got to go by 1. So it starts here, and it can't go backwards, right? It can't go by negatives. So it starts at 3, then goes to 4, then goes to 5, then goes to 6. Okay, so here we put in a 3, we get 6 plus 9 is 15. We put in a 4, we get 8 plus 16 is 24. We put in a 5, we get 10 plus 25 is 35. And we put in a 6, we get 12 plus 36 is 48. And we would add those up. And we would get 39, what is that, 74, 82, 122, maybe? Okay? Now, get your calculators out. Your calculators have sigma on them. So we'll make somebody, Jacob Olson, be the presenter. Thanks, Jacob. I think you've done this before. All right. And so Jacob is going to put that sigma in for us. Do the first one. So go to your template. You can see we've got a sigma notation right there. Okay? And so everybody can try this. To be honest, we're not going to have to do this on our calculators very much. I mean, the one on the quiz is going to be pretty much no calculator. Okay? But it's going to be handy for us to check some things here. So we go in, we go I equals 1 to 5, we put I plus 3, we hit enter, and we get our 30. Okay? All right. So, and then, you know, I put the other one in, but we put the other one in, it will come out the same as well. All right. Now, there are also a couple of other things with sigmas that we want to be able to do. One of those is we want to be able to take and do that in reverse. We want to be able to take a sum and write the sigma that matches it. Okay? Now, that's what I'd like to do on this R100 up here. I've got a sum all written out. I'd like to write that in terms of a sigma. Now, these are a little more complicated to write. The ones we're going to do are actually quite easy. Because when you write a sigma, and this is where the patterns come into play. So let's go to our R100 here, and let's write out our sigma here. Okay? Now, how many terms do we have? How many terms do we have that we're adding? 100. The easiest way is to start I at 1 and go to 100. Now, there might be some reason to let it be something other than 1 to start with, but usually we start our I at 1 to 100. Okay? And then we want the formula in here that will generate all those terms. Now, ours are going to be quite easy to do because ours are going to have very nice patterns. And the key to writing the sigma, I know you might think of it as confusing, but really, the only thing you need to worry about in writing the sigma is what in each term stays constant and what in each term is variable. Well, almost everything in here repeats from term to term. There's an F in every term. There's parentheses and a 100 in the denominator in every term. What else is constant? The pi, well, the pi over 100, the width is constant in every term. And also in every term in the numerator is pi. The only thing that changes is the top number of 1, 2, 3, all the way to 100. So what's going to go up here? I pi. I pi. That's right. Okay? And that will be the theme on the sigmas we do. The sigmas are going to be pretty easy to write. Okay? And part of your homework. Now, as we go through this homework, or as we go through these problems today, this is kind of what your homework's like too. Your homework's going to start off with some easy sigmas to expand. And then it's going to start off with some things like this that you have to turn into sigmas. Okay? And they're pretty easy because the pattern is pretty easy to see. Okay? And the I goes in wherever that number is changing. Okay? All right. Now, we've got one more little step to do here. Okay? We've got one more little step to do here, and that before we can put it into our calculator, and that is take it out of our F notation. What does it mean to do F of I pi 100? It means to take I pi over 100 and plug it in to here, right? See, this is why I like F notation, because F notation is the same no matter how ugly or complicated your function is. But now at this last step, we want to take it out of the F notation and plug it into the function. So F of I pi over 100 means take I pi 100, put it here. If this was sine x, we'd have sine of I pi over 100. If this was e to the x, we'd have e raised to the I pi over 100. So what we're going to have here is a sigma I equals 1 to 100. And then we're going to have I pi over 100 squared times pi over 100. And that, then, we can type into our calculator. So we'll go ahead and write that down and then have Jacob type that in. And you guys can go ahead and do it as well. Because that's really the only way to add up 100 terms. The only reasonably quick way to add up 100 terms. We could certainly sit here and add up 100 terms if we wanted to. But it's the only reasonable way to add up 100 terms. And what do we get? 10.49. What is the non, or do we even want to write it? What's the non-decimal?
It's like 6,766 or 67 pi cubed over 20,000.
Like that?
Yeah.
Which would be
10 point.
Let Jacob finish that. There we go. Okay. And as a decimal, what is it? 10.491. Now, compare that, and again, it's easy to get lost in the weeds here a little bit of everything we've been doing. But right, we compare that to the 10.335. Right? Now let's think about what we're doing picture-wise. We looked at some of this yesterday. We got this area. We know the exact area because of the fundamental theorem part 2. But then we said, now let's look at it kind of like we did derivative. We don't know how to do slope at 1 point. Let's do slope between 2 points and let that approximation get better and better and better. Well, that's what we did here. We said, let's do 4 rectangles, and that was an over approximation, not very good. What would be better than 4 rectangles? Well, 100, right? 100 would be better. So 100 gives us this, right? Now, to do 100, we really needed to do the sigma and do all that, okay? But clearly, we got a pretty good approximation. It's a little bit over still, and think about it, all 100 of those right rectangles would be just a little bit over the curve. So we got a little bit of error there. So obviously, 1,000, a million would keep getting better and better. And we'd keep getting closer and closer to this. So what we would like to do now is get exact. Just like we did with slope. We'd like to get exact. So how many rectangles do we want to do? We want to do an infinite. Now, unfortunately, infinity is not a number, so I can't really do it that way. But so what we're going to do is we're going to do n rectangles. So here's the next thing we're going to write. Okay? So we're going to write r sub n. Stay with me now, please. Stay with me now. Okay? R sub n. Okay? We can't do r sub infinity, right? It's not a number. So we'll do r sub n, and we'll let n what? We'll let n approach it. We'll do a limit. We'll do a limit as n approaches infinity, as n gets very large. And we've done limits as n goes to infinity, right? What was one of the things we looked for when we did a limit as n went to infinity? If we had a problem where we had to do the limit as n went to infinity, well, sometimes you would get infinity over infinity, stuff like that, but that was indeterminate. We could still do stuff. Does high powers dominate sound familiar? High powers dominate. When n's getting really big or x is getting really big, high powers dominate, that kind of thing, right? We're just saying what is happening as n gets bigger, bigger, bigger. Okay, well, that's something that's going to come into play down the road, but here we go. So what's going to be different here? What's going to be different? Well, now we're going to add that in later. Let's start from scratch, just like we did R100. We're going to have a width of pi over n, because we're going to have pi minus 0, our total width, divided by n subintervals. So our width is going to be pi over n. What's my first right endpoint going to be? Pi over n, right? We start at 0, we move over pi over n wide. That's our first one's pi over n. So this is going to be f of pi over n times the width pi over n. Plus, what's my next endpoint? If I'm at pi over n and I add on another pi over n, what's that? 2 pi over n, right? The denominator doesn't change. Common denominators. Okay, probably don't need to write any others. Let's write the last one. F of n pi over n. Which again, all makes sense because n pi over n is the same as pi, and that should be our right endpoint. Even though we have an unknown number of rectangles, we still should end at pi. So we still should end at n pi over n. Okay? And, of course, we can't add up an n number of rectangles, but we could do a sigma notation. So as a sigma, this would be I equals what? Looking for the pattern here. How many we adding up? Here we did 100. How many are we doing? N. So we'll go 1 to n. Right? Do a sigma. We're going to add from 1 to n. And look at our pattern. F is in every one of them. There's parentheses. There's an n on the bottom in every one of them. There's a pi over n that's the same in every one of them. And what goes on top? I pi. It goes 1 pi, 2 pi, 3 pi, all the way to n pi. So I pi. So when I is an n, it sounds weird to say, when I is an n, we'll put an n right there, we'll have n pi over n, right? So that is that formula, okay? And now let's take it out of F notation, which means what? Plug that into the function, means square it. So this is going to be sigma I equals 1 to n I pi over n squared. Oops. I pi over n squared times pi over n. Now, we could type that on our calculators. Oh, what the heck. Type it on your calculator. We'll do that first. So let's go ahead and type that onto our calculators. With the n's in there. What do you get?
plus
Do you want to do it?
No. It'd be good without decimals. There we go. Okay, so pi, I'm going to write the pi cubed first, but that doesn't really matter. So we got pi cubed times n plus 1. Am I off the screen yet?
No.
The next thing will. All right. So it's pi cubed times n plus 1 times 2n plus 1 all over, what was it? 6n squared. Now, basically what I've got there is a formula for R4, R100, R anything, right? For this problem, I've basically given myself a formula for R anything. For example, we could just check it. Is it right? R4, we have this. So let's try R4. That would mean 4 would go in for n, right? That's what n is. N is the number of rectangles, right? N's the number of rectangles. So if we put a 4 in here, we'd have 4 plus 1 is 5. 8 plus 1 is 9. 9 times 5 is 45. We'd have 45 pi cubed over 4 squared is 16. 6 times 16 is 96. So we'd have 45 over 96. I'll bet that reduces to 15 over 32, right? Divide each of them by 3. So we would get 15 pi cubed over 32. So that seems to work. And I'm guessing if we put 100 in there for n, it would reduce to that right there. Right? Okay, so that seems to be okay. Now, that's with the calculator. Now I'm saying we could do this by hand. Okay? And here's what we're going to need to do it by hand. First, I'm going to do some algebra to this. I'm going to go ahead and square this, right? So I get I squared pi squared over n squared times pi over n. What would I have on top? I'd have I squared pi squared times pi. Let's write that down. So I got sigma. I'd have, what's that? I squared pi squared times pi. What's that? I squared pi cubed over the bottom n squared times n squared times n, be n cubed. Okay? Now, what can we do with that? Well, there's a couple of properties. If you turn in your book, another little side trip here, please. If you turn in your book to page 357, okay, another little side trip here. At the bottom of page 357, they give us 3 properties of sigmas. You do not have to memorize these. These will be given to you on the quiz, okay? And so you can use them from the book in your homework, and you will need them in your homework. There's a couple of different parts of your homework section where you use these properties. Now, you're not going to have a homework problem where you have to do this whole thing. It'll be broke up. There'll be a section where they're going to have you expand out a sum. There'll be a section where you've got the sum and you're going to write the sigma. There's going to be a section like this where I give you the sigma and you're going to use these properties that we're about to do here. And then there's going to be a section where you do the limit as n goes to infinity, which is the last part we'll do at the end. Okay? So, but that's kind of the different things in the homework. Now this says if you have a sigma of a constant, so 1 to n, you're going to add up that many constants. So constant plus constant plus constant, you have n of them. What's that going to be? Well, it's just going to be n times the constant. Like if I got 8 3's, I'm going to add up. If this was a 3 right here and I went from 1 to 8, 3 plus 3 plus 3 plus 3, 8 times is 24. You just multiply. So that's the first formula. Second formula, if you've got sigma I, well, sigma I means 1 plus 2 plus 3 plus dot, dot, dot. That formula is n times n plus 1 divided by 2. Now, there's kind of an interesting story that goes together with this particular one. As the story goes, I'm not sure it's really true, but this young genius, story goes, his name was Gauss. He was a famous mathematician. But as a child in first grade, he was being punished by his teacher because he was a genius, and so he was bored, maybe, or something. I don't know. He was talking when he shouldn't have. So the teacher sent him to the corner and said, add up the numbers from 1 to 100. Now, he's a first grader, or second grade or whatever. Add up the numbers from 1 to 100 and don't come back until you're done, thinking that this would keep him occupied for quite some time and then she wouldn't have to deal with it. Well, he goes to the corner and in like 10 seconds he comes back and he has the answer. Okay? How did he do it? Well, he did it like this. 1 plus 2 plus 3 plus dot 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 plus 98 plus 99 plus 100. And what he noticed is that he could pair the numbers up. Those two would add up to what? 101. These two would add up to 101. How many pairs of those would you have? You'd have 50 pairs of numbers. You'd have 50 101s. So you take 101 times 50, and you've got your answer. And he comes back. Well, if you look at this, I don't know that that's a true story, but that's how the story goes. Well, if you look at this, if I have 100, what would this be here? This would be 100. The n over 2 would be the number of n over 2 would be the number of pairs, right? So that would be the 50, right? 100 divided by 2 is the 50, and then there's the 101, your last term plus your first term, and that's where they got the 100 plus the 1. So that is the formula for adding up consecutive integers, okay? And if you have a sigma I squared, 1 plus 4 plus 9 all the way out to n squared, that adds up to n, what is it? I can't remember that one. That's why I'm not going to make you memorize it. N times n plus 1 times 2n plus 1 all over 6. Okay? So if we were going to add up the first 100, the squares of the first 100 terms, we'd put 100 here, 100 here, 100 here, work that out. That's what the sum would be. Okay, so we're going to take those three formulas. You don't have to memorize them, you just have to be able to use them. And we're going to take those and we're going to go, oops, and we're going to apply that to where we're at right here. So, I've got this sigma. Now, it's probably not shocking to you, if you kind of are seeing at all where we're headed with this, that the properties of sigma, or some of the properties of sigma, are very similar to the properties of integrals. And one of the properties of sigma is the same as we can pull out a constant. Now, in this particular thing right here, we got pi's and i's and n's. What are constants and what are variables? Tell me the constants. Pi is a constant. What else is constant? N is constant, right? N is the number of subdivisions. That's not going to change throughout the problem. N is the number of subdivisions. It is a constant. What's the variable? I is changing. So we can pull in front pi cubed over n cubed and be left with sigma I equals 1 to n I squared. Right? Now we just saw over there in the properties that sigma I squared, so let's write down pi cubed over n cubed, and we just saw that sigma I squared is equal to what? N times, it's at the bottom of page 357, n plus 1, 2n plus 1, all over 6. Now, you can kind of see we're gonna get it, aren't we? I mean, this is, remember, this is what we just got on the calculator. What's going to happen here? 1n here is going to cancel one of those n's over there. Look what you got. You got pi cubed, n plus 1, 2n plus 1, all over 6n squared. Same thing we had right there. Okay, now, what's the only piece that's missing? Come all the way back to the beginning. We want the actual area under this curve. We don't know how to do area under a parabola, but we do know how to do area of a rectangle. So let's do 4 rectangles. Oh, that's not very good. Let's get better. Let's do 100 rectangles. That's better, but not good enough. How about we do an infinite number of rectangles, right? So now we've done n rectangles. Now, again, don't get lost. This is the area. This is the sum of n rectangles. What do we want to have happen with n? We want n to go to infinity. What we want to add to this is we want to add the limit as n goes to infinity of this final answer here, which was pi cubed. Now, what happens, focus in now, What happens when you do n goes to infinity? What do we want to look at? What's one of the things we often look at? I said it earlier. High powers dominate, right? So on this particular sum right here, what's the high power going to be on top? We can't forget the pi cube, so I brought that along. The high power on top is going to be what? Well, there'll be a 2 on it, right? So it'll be 2n squared. The other stuff doesn't matter, right? Because high powers dominate. What's the biggest power on the bottom? 6n squared. Now what? What happens? N squareds cancel. You get 2 pi cubed over 6, which is 1/3 pi cubed.
Oh my God. So excited.
I feel like this is like David Reed just.
It's just this part where David, yeah, almost made me cry. Well, I mean, we got to this point, and then he's like, and then he says, what did he say? He said, "Oh, is that the big deal?" Or something like that, or something. And I said, "Well, if you have to ask, you know, it must not have been that. It must not have been that big a deal." But look at that. I mean, there it is. And we could put this all into our calculator. Go ahead and get the calculators out again, so you can see it on the calculator. But the calculator is just kind of magic. I mean, where does all that come from? This, you actually had your hands on.
Why can't we do
Might seem well, yeah, why can't we just stop here? Yeah, let's just do that. Yeah, no kidding. All right, so, okay, go to the calculator. Let's just see what this would all look like. So, Jacob, just arrow to your to right here, and hit enter and just go up and grab this. Hit enter, and now arrow to the front. Oh wait, this probably isn't going to work. I'm sorry. Delete that. Delete that. Highlight that. Delete it. Good. Or just hit enter. Just hit enter. Just hit enter. Yeah, just hit enter. Now go to the limit. Go to your template and do the limit. We got to do the limit. We got to put it out in front. It doesn't work good. So go to your limit. Last one down there on the bottom. Okay. And now we want n to go to infinity. Okay, go to your template again. Yeah, there you go. Or not, yeah, not the template. Okay, now arrow up in the parentheses. And now arrow up again and grab that. Hit enter. There you go. There you go. And now hit enter. Okay? And there it is again. Right? Now that, see, to me, that's not as exciting because that's, I mean, the calculator did all the work there. However, what we've said now, okay, think about what we've just done. This is it. This is our definition of the integral. Basically, the definition of the integral says that the area under the curve is equal to an infinite number of rectangles. I mean, in plain language, that's what it says. The area under the curve is equal to adding up an infinite number of rectangles. All of our work has been how to mathematically write the words adding up an infinite number of rectangles, because that's what this does. Now, there's one cool thing left, I think. I think you're going to like it. Well, yeah. Okay, so back to this. So what we're saying, what we want to do, is we know we're going to need a limit. Okay, as n goes to infinity. So finding the area under the curve is the equivalent of. Now remember, and this was just stuff I told you. I said, hey, there's this squiggly s thing. Don't worry about it. It's called an integral from a to b. Remember the dx? The dx, what did I tell you about the dx? It's just kind of there. It means with respect to x, blah, blah, blah. Well, actually, there's more to it than that. There is more to it where this dx comes from. It's not just with respect to x. Okay? And it comes from this. Now, what we just said is that the definition of a definite integral is the area under the curve, which means adding up an infinite number of rectangles. So, limit as n goes to infinity, sigma, and now what we want in here is rectangle areas. And rectangle areas mean length times width, height times width, height times width. So if we go back to Riemann sum, here is And this is how it all comes together here. Here's our Riemann sum right here. So there's our first area, there's our second area, here's our nth area. How can I write the sigma for this? Well, let's see. Everyone has an F, every one of them has parentheses, everyone has a C, everyone has a delta X. Where's the I going to go? The subscript. So back to here, my sigma is going to be F of what? C sub I times delta X sub I. Because what this is your height, this is your width, right? And we're going to do an infinite number of those. Now look at those two. And there's some similarities here. This is a Greek letter S. This kind of looks like an S. I know, it's a stretch, but still. Look, and look at this. F of X. This F of X was our function, but and look at that. The dx and the delta X. The delta X is the width. Now, the dx that's where it comes from. It does mean something. Matter of fact, I hope from now on you never look at a definite integral the same way again. When you look at a definite integral, you see function height times width. You see an area there. You see a rectangle area. You see height times width. Now, when we actually work the problem, we don't do anything with the dx, right? We don't do anything with it. We won't from here on out, really. It will help us in units. Thinking about the dx as width is going to help us in story problems when we get into units. So it is going to be important. But think about the width of the rectangles as you go to infinity here with n. What happens to the width? It gets smaller and smaller and smaller. If you go to an infinite number of rectangles, your width gets smaller and smaller and smaller. And if you really could ever get to an infinite number of rectangles, what would be the width? Nothing. And that's why in the actual definite integral, the dx really doesn't do anything. It really doesn't have a value or a quantity because it's kind of like the width going to 0. Okay? But if we leave it there, it's with respect to, it helps us with those kind of things. But always, when you look at a definite integral, you think of it as coming from this. Okay? Does it really solve problems for you any differently than what we've already been doing? Not really. Okay? We'll still have fundamental theorem part 2. If we need to approximate an integral, we'll talk about ways to approximate. For example, I know the calculator can give you this one exactly. Type this on your calculator. Do this integral for me here. Do the integral from 0 to pi sine of x squared. Type that one into your calculators and tell me what it gives you. I'll be honest, I don't know. I know on the old calculators, I just haven't done it on these new ones.
There's like 0.77.
You get a decimal? Okay. How come you didn't have to? How come you didn't have to? Go ahead and type that one in, Jacobs. Yeah. How come x squared, sine of x squared, dx? How come you didn't have to hit control enter? How come it gave you a decimal? There's no antiderivative of this. So even the calculator can't find the exact answer because there's not an antiderivative. So how did it get this? It did an approximation. It's programmed to do 1,000 right rectangles or 1,000,000 trapezoids or whatever. Actually, it's programmed to get to within a certain degree of accuracy. Okay? Yeah, I mean, it's terrible. It can't get it exactly, I agree. No, it's programmed to get within like 12 decimal places of accuracy. But then the question would be, how would it know it's 12 decimal places accurate if it can't find the exact answer? That's chapter 6. Excellent. We'll get into that.
Is it like where it does it over and over again until it starts like like we did with the new
Not really. I mean, it.
Oh yeah.
Now, there are techniques that it'll do. There's formulas that'll say for this integral, here's how many you have to do to get within this degree of accuracy, and that's how many it does. Go ahead.
With the definition, do we have to write I equals and then the n on top?
Did I leave that off?
Yeah.
I did.
And
Thank you.
Will it always be 1?
Yes. Well, I mean, I equals 1 to n would mean f of c. Well, yeah, it would be 1 because this means our first subinterval. The I is the number of the subinterval. So we'll go for, yes, and that's very important. I make sure you put that on there. It's improper to go 1 to infinity on a sigma. You can't put an infinity up here. It's got to be numbers. I mean, we know what you mean, but we really need 1 to n, and then you do the limit as n goes to infinity.
Okay, if you were using like left side rectangles, would you use I equals 0?
Not in this here. Not in this one. But you're right in your sigma over here. Okay? If I was to, if you want to, and this is actually kind of important, not necessarily on today's assignment, but as we get into these some more. If I would have changed this here to a 0, not on the same screen. If I was to change if I was to change this to a 0 right here and change this, that would change this to an n minus 1. Now look what would happen here. So if I put a 0 in for I first, what do I get? I get f of 0. And then I put a 1 in, I get f of pi over n. And then put a 2 in, I get f of 2 pi over n. How would that have changed this? My first one would have been, instead of pi over n, would have been 0. And then pi over n, and then 2 pi over n. Well, what am I looking at there?
Left.
Those are left rectangles instead, right? Because my integral starts at 0. So if you're doing left rectangles, the first one would be 0. So that actually is a true statement. Your sigma, if you go from 1 to n, looks like this, is right rectangles. If you take that same exact formula and just change it 0 to n minus 1, you have left rectangles. So the sigma for left is pretty easy to write once you have the right. You just change it.
And if you were going to do the n approaches infinity, wouldn't it still be just n because n or infinity minus 1?
Well, the difference here is, yeah, that's still infinity. Yeah, and actually you'd still have the same formula. 0 to n minus 1, everything would be the same. And it'd just be an infinite number of left rectangles, which would come out the exact answer from below, right? This was too much, this was a little too much, and then we were getting closer and closer and closer until we got the exact. Okay, so here's the homework. So go ahead and get out your assignment sheet, and we've still got about 15, almost 20 minutes to get started here. And the LH packet you need here is an older LH packet that I've given you before. It's got 279 at the top, page 279. Okay, now it's going to be pretty obvious because it's got the first problems are sigmas. So you're going to be able to tell you got the right one. Okay, so it's an LH packet, page 279. Okay, on the assignment sheet, it's just the line right below the one you did for today. Now I would like you to do 25 and 28 from the book. They don't take very long, but they were tables of values. They were like the one we did in sample 2 today, at number 41. Okay, with those tables, and just do those, and they're pretty straightforward now that you've seen one of those. But I do want to talk about the LH packet really quickly, and maybe have you write down a couple notes to yourself, because it is easy on this assignment to really kind of feel lost on it, and so I want to help break it down for you just a little bit. Okay, has everybody got the LH? So look at the LH packet, if you would, for me, page 279. And we're doing like 1 through 8, and then essentially it's 9 through 35 odd, but I always write those things weird, but. Okay, so everybody looking at the LH packet, please? So you might make just a few notes, but I just want to kind of go through because there's a real sequence to how the problems go. So the first 8 are just some simple sigmas. Plug in your i's, expand them out, write the sum. It's not intended that you use your calculator really for hardly any of this, quite honestly. Okay? Because, quite honestly, this book was written before any of these calculators ever existed. So, and the quiz next week is pretty much no calculator. Okay? So 1 through 8. Plug those in, expand them, get the sum. Okay? The next section, 9 through 18, you're supposed to write the sigmas. So those are, but they're really pretty easy. I mean, they look very complicated, but they're not. I mean, it's just like what we did here, where you look at this and you look at all these terms and you're like, oh, the 100 doesn't change, the pi doesn't change. The only thing that changes is that number up there. And so we're just going from there to writing this sigma. Okay, so it's really not too bad. All right. Now the next section, 19 through 24, it says use the properties of sigma. Now the properties are those ones on page 357. So that'd be these properties right here. So they give you a sigma with an I, like a 19. On 19, you would just pull that I, that 2 out in front. On 19, you just pull that 2 out in front, and you'd have sigma I. And then you would just use the formula up here for sigma I. And you'd plug a 20 in for the n. Okay? On number 22, you would FOIL that out. I minus 1 squared. You'd FOIL that out. And you'd have I squared minus 2I plus 1. And you would just break that into 3 separate sigmas. One would have an I squared, one would be an I. See what I mean? So you're just going to take those sigmas and then apply these formulas. Okay, the next group then says, do the limit as n goes to infinity. On 25 through 30, do the limit as n goes to infinity. Well, that's what we did down here, right? This is where we do the high powers dominate. So on 25 through 30, it's just a matter of high powers dominate. They give you a thing that looks kind of like this, and you do that. And then 31 through 36, that last group kind of puts those last two things together. They give you the sigma, so you're supposed to break it apart and use these properties, right? Use these properties, you'll get these things with n's in them, and then do the limit. Then do the high powers dominate. So use the properties and then do the high powers dominate. So that last section kind of brings together the two previous sections. Okay, so hopefully that gives you enough to get going. And then if you have more questions, we can talk tomorrow, or you can come in and see. All right, so the rest of the time is yours to work. Yes.